Hello, everybody. Welcome back. Today we're going to be looking at subunit 9.9, which relates a new concept for us, something called cell potential, to a concept that we already know about, Gibbs free energy. So let's get started. All right, so let's just think back to our last subunit where we learned all of the different parts and pieces of what's called a galvanic cell, fancy name for just a battery. Remember that we have two half cells that involve a redox chemical reaction, linking those two half reactions, one for reduction, one for oxidation, causes electrons to flow through a wire, and we get some voltage, some electrical power out of this situation. And that's what we're going to be looking at today. Cell potential is a fancy term that means how much voltage are we getting out of this galvanic cell, okay? And there's a little bit of vocabulary here, okay? Because we are a chemistry class, we are going to use the term cell potential, whereas physics people might use the term electromotive force or EMF, okay? We're talking about those electrons moving through the wire. Now, my physics friends tell me that this, what we call a cell potential, what they call in physics an electromotive force, isn't actually a force moving the electrons, but you can sort of think of it that way. It's sort of, just to sort of wrap our heads around it, a force that is either pulling the electrons towards the substance being reduced or pushing the electrons away from the substance being oxidized. It is not a force, it's really just a difference in potential, but we can think of it that way. But ultimately, guys, a cell potential is the amount of voltage coming out of this electrochemical cell. It is measured with a voltmeter. We saw that in our diagrams for galvanic cells in the last subunit. It's measured in volts. And you will see this symbol, this variable, E, capital E with a subscript cell. Sometimes you will see it written like, let me show you, like this sort of fancy curly Q cursive capital E with a subscript cell. Sometimes you'll see it written like that. It means the same thing, okay? It's the voltage, or what we're going to call the cell potential, coming out of an electrochemical cell. So all kinds of different substances can be oxidized and reduced. There is one particular substance, hydrogen, that is considered sort of the reference potential. It's just the arbitrarily decided substance that is going to have a voltage of 0 volts. And that's all this is trying to illustrate here to you. Your teacher is likely going to provide to you, or maybe it's in the back of your textbook, some sort of a table that looks like this. Okay, so let's look at what's going on in this table, okay? If you look at the title, it says standard reduction potentials. So if you run your eyes down this chart, and again, your teacher has likely provided for you some sort of chart like this, I want you to notice that the electrons in all of these half reactions are all on the reactant side. And that's because all of these half reactions are written as reductions. That's what the title of the table says. So for example, that very first half reaction at the top is showing fluorine gas gaining 2 electrons and being converted into fluoride ions on the product side. That's in aqueous form, so that's a reduction. And if you look at the potential just to the left of it, that tells us that when this reduction half reaction takes place, 2.87 volts would be produced. Okay, so first and foremost, where are the substances in this chart? Where are the substances that are being reduced? Well, they are all on the reactant side. Okay. Now, this is something we're going to get into today. It says, which has the most favorable reduction potential? Favorable. That is a word we have seen before when we were talking a lot about Gibbs free energy. And I want to tell you that in terms of potentials, in terms of electrochemistry, the most favorable processes have the most positive potentials. Okay, let me say that again. The most favorable processes, favorable meaning spontaneous, likely to happen on their own, the most favorable processes are the ones that have the most positive potentials. If you look in this table in front of you, you can see that some of the reduction potentials are positive, some are negative. We can see that there's that one 0 for hydrogen as the reference potential. So which one is the most positive? Well, that would be fluorine gas. Okay, that first half reaction occurs the most favorably, whereas look at the very, very bottom of the chart. Lithium ion being converted into solid lithium is the least likely to occur favorably because it has a very negative potential. Now, if you will recall back from when we talked about how galvanic cells work, they involve redox reactions. So you have to have one reduction half reaction and one oxidation half reaction. So the question is there another table for reduction half reactions? No, there isn't. The way to turn a half reaction, a reduction half reaction, into oxidation is to simply flip it around. Okay, so where are the substances being oxidized? We can look at this table differently if we want to by flipping all of these half reactions around. For example, take that first half reaction at the very top of the chart. If I flipped it around so that 2F- is now a reactant and F2 gas and the 2 electrons, that's on the product side, that would be a half reaction written as an oxidation. So if you flip, if you flip all of these half reactions around, you can turn all of these half reactions into oxidations. Now, what happens to that potential value if you flip a reaction around? It changes sign. Okay? So here's the question. Which half reaction on this table would have the most favorable oxidation potential? So what I want you to do is imagine this whole chart with every half reaction flipped around and every potential value opposite in sign. But guys, the same law holds here. Whatever has the most positive potential is the most favorable. So what is the most likely thing on this chart to be oxidized? That is going to be solid lithium. Not lithium ion, lithium solid. Okay, so look at that very bottom reaction. If we flip it around, solid lithium is being converted into lithium ion and 1 electron would be released, and the potential value would now be positive 3.05 volts, and that's going to be the most positive one on the table. Okay. So here's the thing. Let's bring this to a galvanic cell situation. Okay. Let's say we are dealing with this redox reaction. It's actually, I think that's the same reaction we dealt with in the previous subunit as an example of a galvanic cell reaction. The total cell potential, meaning the total voltage that's going to be coming out of this battery, is going to be the sum of the potentials from each of the two half reactions. Okay? Now, Do you need to memorize any of these potential values? Absolutely not, okay? If you're working problems in your class, again, you'll probably have access to a table either in your textbook or your teacher will provide you one. If it's a question on the AP exam, the College Board will give you the half reactions and the potential value that goes with it. They will always give that to you. There's nothing to memorize, okay? But here's the thing that is so important for you guys to understand. One of those half reactions is going to have to be flipped around. Let me explain. Those tables, for whatever reason, are always written as reductions. I don't know why, okay, but they're always written as reductions. Remember that a galvanic cell includes one reduction half reaction and one oxidation. So you'll have to flip one of those half reactions to turn it into an oxidation. Okay, so here's the question. How do you know which half reaction should be flipped around? Okay, well, this is really important. This is one of the big take-home messages for today's lesson. If we're talking about a galvanic cell, remember galvanic is sometimes called voltaic, the overall, the total cell potential will always be a positive number. You have your two half reactions, you have to flip one of them because you need an oxidation as well as a reduction. When you add those potentials together, galvanic cells will always, always, always have a positive total. So what does this look like in practice? We're going to work this together. Okay. It says write a balanced cell reaction and calculate, and there's that capital E, the cell potential for the cell using your standard reduction potential tables, okay? And then we're given an equation. And you might say, well, why do we have to write a balanced cell reaction? They've already given us the cell reaction. Well, this is what's actually called like a skeleton equation. It might look balanced to your eyes. It's actually not charge balanced. So here's how we're going to approach this. Okay, what I'm going to do is I'm going to have my standard reduction potential table in front of me. And I'm going to find the two half reactions that are involved in this redox reaction. So the first thing I'm going to do is I'm going to look up, I'm going to try to find the half reaction that involves chromium +3 and chromium +2 ion. They may not be written in that order, and that's okay. But I'm just literally going to copy this down straight out of my reduction potential table. I'm not changing anything. And out to the side, this half reaction has a potential of negative 0.41 volts. Okay. Next, I'm going to find the other half reaction. So the one that involves magnesium solid and magnesium ion. Again, it may not be in the order that it's written on the screen. That's okay, no big deal. I'm just going to write it exactly as I see it in my chart. Just copying it down, not changing anything. And the potential for the magnesium half reaction is negative 2.36 volts. Okay, so these are my two half reactions. Now remember what I said. We know that we will have to flip one of them. A galvanic cell does not involve two reductions. It's one reduction and one oxidation. The question is, which one do we have to flip? Okay, now, some of you have probably already figured this out. If you look up here in that skeleton equation, I can see that solid magnesium is on the reactant side, and the way that I have it written here, it's not. So I can see, yeah, that's going to be the one that I'm going to flip. But Guys, let's say you did not have this, okay? You were not given that skeleton equation. All you were told is these are the two half reactions involved in this galvanic cell. What is the balanced reaction that's going to occur? Here's how you know which one to flip. Remember, the total, after I've flipped one of them, the total cell potential must be positive, okay? So I can see that it's going to be the magnesium reaction, okay? Because what's going to happen, guys, is when I flip that magnesium reaction around, its cell potential is now going to be positive. And if you add those two numbers together, we're going to get a positive total. Whereas if I had flipped the chromium reaction around, it's going to leave me with a negative total. So let me rewrite the magnesium reaction flipped around so that it can be written as an oxidation. Okay, now my reactions look better. I've got one reduction, one oxidation. I have adjusted the potential, so I changed the sign. Are we now ready to add these two reactions together? Not quite. This is actually review back from Unit 4, I think, when we add reactions together like this, half reactions in a redox situation. Guys, remember the number of electrons has to cancel out. Electrons have to be on opposite sides of the arrow, and they have to have the same number, and right now they don't. The chromium half reaction has 1 electron, the magnesium has 2. If you recall back from previous units, what do? I'm going to multiply this chromium half reaction, the whole thing, times 2. And now my electrons will cancel out. Okay, pay attention for a minute here, guys. To make the electrons cancel out, I multiplied that whole chromium half reaction times 2. However, I am not going to change that potential value. It is going to stay at negative 0.41 volts. Potentials, voltages are not extensive. If you change the amount of reacting material, it has no effect on the amount of voltage. So I'm going to leave that number alone. But now my electrons will cancel out. So here is my properly balanced cell reaction for this galvanic cell. And it's not only element balanced now, it's charge balanced as well. And if I add those two numbers together, now I can write this word cell, okay, because this is the value for the entire galvanic cell. I add the numbers together, and there's my total cell potential. Okay. Just a little aside here, I forgot to mention this earlier. If you'll notice, every time I write that capital E, I'm putting that little degree symbol next to it. Just to review with you, that degree symbol means under standard state conditions. Remember, that means 25 degrees Celsius. Any and all gases would be at 1 atmosphere. Anything that is aqueous would be at a concentration of 1 molar. So just a refresher on what that means. So let's kind of bring this all together. So if we're talking about a galvanic cell, let's give a complete description, okay? Probably the most common thing you'll be asked about a galvanic cell is to come up with the balanced cell reaction and calculate the cell potential. And that's what we just did on the previous slide. If you're given a diagram, like we were in the last subunit, you'll very often be asked to draw an arrow showing the direction of electron flow. Remember, the electrons will always flow from the half cell where oxidation is taking place to the half cell where reduction is taking place. And also very often you'll be asked to identify which half cell contains the anode, which one contains the cathode. Remember, anode is where oxidation is, cathode is where reduction is. Electrons always flow from anode to cathode. So what I would like you all to do is a little bit of practice of what we were just doing. I have provided for you the half reactions involved, so you don't have to look them up, okay? But there's two questions here, two galvanic cells. I want you for each one to come up with the balanced cell reaction and the total cell potential in each one. See how you do. All right, so let's start with number one. And I tried to make this as neat as possible. So in the first two lines, I just had those two half reactions written out, okay? And I figured out that I was going to flip that aluminum half reaction, okay? Again, how did I know that? Because when I flip that aluminum half reaction, the potential becomes positive 1.66, and when I add my two potentials together, that gives me a positive total, which we'll always have for a galvanic or voltaic cell. Please notice I did have to multiply the copper half reaction times 3 in order to get those electrons to cancel out. I have also labeled which half reaction contained the anode, which one contained the cathode. And let me tell you guys a little secret here. Whichever half reaction you flip is where your anode will be, always. Because think about it, why did you have to flip that reaction? You flipped it to turn it from a reduction to an oxidation, and wherever oxidation is, that is your anode. Okay? So that one was pretty straightforward. The second question was a little bit more involved, and I tried to make this as neat as possible. It's the same process, it's just there's a little bit more stuff going on here, okay? So first and foremost, I knew that the manganese, or that permanganate MnO4 minus, that half reaction was the one I would need to flip, again, because it would change sign and the total, when I add the two potentials together, would still be positive. So I knew that was the one I needed to flip. Now this problem was a little bit more complex because to get the electrons to cancel out, I had to multiply the permanganate equation times 2 and the ozone equation times 5. But guys, again, please notice that I did not touch those potential values. Just because you multiply a half reaction, leave the potential values alone. Now look at the bottom part of the screen here. The electrons certainly cancel out, but in this example, there's other things that can cancel out as well. I can see that some of the H+ ions canceled out because H+ was on opposite sides of the arrow, and some of the water molecules also canceled out, okay? So it's the same process we were just doing. There's just a little bit more stuff, okay? Again, the reaction that I flipped, that permanganate half reaction, that ended up being the anode. And one thing I want to review with you all, just from the last subunit, neither one of these half reactions involves any solid substance. Now remember, a galvanic cell has to have two solid metal or solid electrodes to operate properly. Just to review, what do you do if one or both of your half reactions does not involve anything solid? In this case, both of these half cells are going to have an electrode that's made of either platinum or graphite, because the permanganate half reaction, everything is in aqueous form. And in the ozone half reaction, both ozone and O2, those are both gaseous substances. So again, we'd have to use a platinum or a graphite electrode. So that's just review from last subunit. All right. So we're going to start now pulling in the concept of Gibbs free energy. Remember what we said, galvanic cells are always going to have positive cell potentials. And a little bit earlier in today's lesson, we said that things that run favorably, most favorably, have the most positive cell potential. So favorable, that's a term we used a lot when we were talking about Gibbs free energy. So guess what, guys? There is an equation that relates cell potential and Gibbs free energy. You do not need to memorize this equation. It is on your formula sheet. Okay, but let's just go through this. Okay, delta G, we know what that is. That's Gibbs free energy. This lowercase n, it says number of moles of electrons. Let me translate that for you. In the problems we were just working, the number, whatever the coefficient was for the electrons that we canceled out, like in that last problem we did, we canceled out 10 electrons on both sides. 10 is the number I would then plug in for that lowercase n. It's however many moles of electrons got canceled out when you added the two half cells together. That capital F is something called Faraday's constant. You do not need to memorize it. It is on your formula sheet. Okay? And of course, that capital E is our cell potential. Okay, so now we have an equation relating cell potential and Gibbs free energy. And guys, if you think about it, let me pull both statements up here. I'm actually going to start with the second one. Galvanic cells always have a positive cell potential. So that number is going to be positive. Faraday's constant is also positive. The number of moles of electrons is also going to be positive. And then they get multiplied by a big negative sign. That is going to result in a negative delta G. So ladies and gentlemen, let's pull some concepts together here. If a cell potential is positive, that's going to result in a negative delta G value. What does that mean? That means favorable or spontaneous. So galvanic cells are like magic. You hook up these two half cells together and you just stand back, and on their own, spontaneously, without any outside intervention, electrons flow and we get electrical power. That's very cool. Now what we're going to see in the last subunit in Unit 9 is when cell potentials are negative. That's what's happening in electrolytic cells. That would be a non-spontaneous or non-favorable process, but we'll get to that. Okay. So I want you guys to try one final problem. This would be a perfect example in free response. As I said, guys, you do not need to memorize any of the potential half reactions or anything like that. They would be given to you in a table, just like you're seeing in front of you. You're given a diagram of a galvanic cell. Okay, should look familiar. We did a similar one, maybe even the same one. But now you have these two half reactions. It says write the balanced equation, determine the cell potential. It asks you a question about the concentration of the aluminum ion. It asks you to calculate delta G, and then we're going to pull this back from a previous topic. We want you to relate that to the equilibrium constant. So pause your video, see how you can do with these. All right, so let's take this problem part by part. Part A asks us to write the balanced equation for this reaction. Now, if you look up at the top here, guys, there's a key word here. Let me circle it. Let me change this to red. Right here. Remember the word voltaic? That's just another word for galvanic cell. And remember, we said that galvanic cells have to have a positive total, so that enables us to know which half reaction to flip. So I knew that I would need to flip that aluminum half reaction. I did have to adjust my coefficients to make sure that the electrons would cancel out. But what you're seeing right here is our balanced cell reaction, our redox reaction. And once I change the sign of that aluminum half reaction, added the two potentials together, there is my total voltage. Okay, now if you go back and look at that balanced cell reaction that we wrote, that enables you to answer the question in part C. Does the concentration of that aluminum ion increase, decrease, or remain the same? If you look at your answer to letter A, the aluminum ion was on the product side. It's being produced as this galvanic cell runs, so the concentration should increase because that aluminum ion is a product of the reaction. Part D asks us to calculate Gibbs free energy. Well, guys, we're using that equation, that new equation that we just learned. Okay, and here it is. Let's just review. That lowercase n, that is the number of moles of electrons that we canceled out when we added the two half reactions together. F is Faraday's constant, and that capital E is, of course, the cell potential we calculated in letter B. We put it all together, and just so you guys know, when you plug numbers into this equation, the units that come out automatically are joules. You did not have to put this final answer into kilojoules. That's just your preference. You do need 3 significant figures. But I want you all to notice that the answer to letter D is negative. This was a voltaic galvanic cell with a positive cell potential. That's going to result in a negative and favorable delta G. Okay, last part. Is the value of the equilibrium constant greater than, less than, or equal to 1? Well, this goes back to a previous concept. If delta G is negative, let's review what that means. That means the forward reaction is favored. That means that the K value is going to be greater than 1. A negative delta G means that products are favored. That's going to lead to that products over reactants ratio being in favor of the products. So K is going to be greater than 1. All right, so I hope you now have a sort of fuller picture of what's involved in a galvanic cell, not just the bits and pieces of it, but also what you can get out of it. One final thing I want to say about galvanic cells is in all of these problems we've been doing, you may have noticed that the voltages we calculate are not very large numbers. And you might say to yourself, well, how does a battery ever power like a car, for example? Because you obviously need a lot more voltage to power a larger piece of equipment. What they do is they take multiple galvanic cells and they connect them in series, and all of those individual cell potentials add together, so you get a much greater total voltage, just in case you were wondering. So I hope you all have learned a little bit of something today, and I look forward to seeing you next time.